So, I started another equation which is a wave equation. So, the wave equation was dt d phi is minus c dx phi. Now, this solution we know, I mean these are exactly solvable problems, but it illustrates the idea how to start it. In fact, all the big mathematicians, they started devising new schemes by solving this simple equation. So, this equation, let us try to see what are the issues when I try to compute numerically. So, my exact solution I know is superposition of waves omega t, and omega is kc. That you can do, no? I mean you can just substitute here and then you will get the omega, okay. Minus I omega equal to minus c I k. So, omega is kc, okay. Okay, so this is what I started doing in the last class. Now, let us do Euler forward. Okay, so let us just start from trying to solve it Euler forward. Now, this is a separate equation, okay. This has different conditions than that. So, I have to write down again this discretization is same. I am just discretizing like exactly like this. So, d phi I dt minus c, now derivative. Now, this derivative I can compute in many ways. Now, that is where math departs from numerical schemes. Some numerical scheme will give you the correct answer, some will not. So, mathematics of course you get only one answer, whatever you do. In fact, you apply different methods, you will get these answers. But in numerical schemes you may get different answers. Some are correct in the sense approximately correct, some are not even correct. Like I expect a wave solution, my solution will be blowing up if I do numerically, okay. So, if I apply this computation, now central difference scheme. So, what is central difference scheme for the first order? So, phi I plus 1 minus phi I minus 1 by 2h. Now, how many equations I got? Well, you have to specify the boundary condition here as well. So, you can set same boundary condition like maybe a string attached at both ends, okay. So, then the string has amplitude 0, which is I set it to 0, or I could have periodic boundary condition. So, this wave is moving, no. So, if wave is moving, then the boundary condition could be, so let us put it here. So, it is better to think of periodic thing than a circle, periodic. So, start from 0, 1, 2 and this is n minus 1. So, n minus 1 is not same as 0, okay. Now, I can solve all of them, okay. But when I compute derivative, I have to choose, for example, I want to compute derivative here. So, which are the 2 points I should choose? 1 and n minus 1, the end other end. If you want to take derivative here, then I should choose 3 and 1. So, circle is a very nice way to visualize periodic boundary condition. So, you can set it up periodic boundary condition or vanishing boundary condition here. Now, this equation, if I try to test stability, so let us test stability for this condition, this scheme. So, I am going to do Euler forward for time this one. So, this is called central difference and Euler forward. So, phi I n plus 1 minus phi I n is equal to minus c delta t phi I plus 1 minus phi I minus 1. This computed at n. So, let us put h here. Okay. So, now let us plug in this formula. So, e to the power I k x tends to cancel. Now, please recall that this point is in terms of x, this is x, this is x plus h, and this is x minus h, okay, because the difference is h, fine. So, when I substitute for I plus 1, what should I substitute in terms of this? So, f t e to the power I k x plus h. Now, this one x minus h. So, minus f t e to the power I k x minus h. And this side, now this is for time index, n is this bracket, that is why I am making a separate notation n bracket, this time index, but this is the space index. So, both of them will have e to the I k x, so e to the power I k x comes out, and this is in fact f n plus 1 later time, and this is only function of time. So, I do not put space index, minus f n is equal to minus c delta t by h. So, e to the power I k x is getting cancelled. So, it better be, because I want to get rid of the x dependence, and I see how f will change with time. So, how will f change with time? So, I will have f n plus 1 minus f n equal to minus c delta t by h. F is outside, so I will get e to the power I k h minus e to the power minus e. Okay. So, this is f n. F t means a time t means f n. This is time t plus delta t. Okay. So, now we can simplify this. F n plus 1 is f n. So, I am going to take this right hand side and take things common. So, 1 minus c delta t by h. Now, this is going to be sine k h. So, 2 I sine k h. Okay. So, this is the behavior of f. Now, is it stable or unstable? It is unstable because this has magnitude greater than 1, real part and imaginary part is greater than 1. So, my f will grow, yes, because the magnitude of, so you take a mod of f n plus 1 is mod f n and mod of this, and this is growing. So, modulus is growing. So, time dependent part here you can see the time dependent part is e to the power minus I omega t, omega is real. So, it is not growing, it is oscillating, but here it is growing. So, this is not a good solution. Okay. So, Euler forward I say, well, I put everything right, but I am not getting the right answer, but mathematically this is unstable, and that is why we need to worry about stability for our differential equation. Okay. So, to overcome this, if I want to use this scheme, one idea is for this code we will not dig so much into stability, instability, all that. So, if you use, so this is Euler first order, use Euler second order. Okay. You can use, I mean your answer will be somewhat okay. Euler second order, I need to start from here and try to prove the stability. It turns out there are some delta t's for which it is stable. This is unstable for any delta t, whatever delta t you use, this is a bad scheme. But maybe I can do better here. Instead of using say first order, say central difference, I can use higher order schemes. You know, so that's how you solve it yourself, saying, well, let me use a better scheme instead of going through proof and trying to do it. But let me just show you one scheme which is same order, first order, both are first order. Well, this is second order, but this is first order. Euler is first order, error is delta t squared, and this is second order because its error is h cube. Okay, so this pretty famous one, if you want to stick to only first order, this is called Upwind scheme. I am just going to show you. This is famous among fluid dynamics. It is not accurate, but it gives you stability. Okay, you might have heard this if you have done any CFD, computational fluid dynamics, then it is used quite often. So, in this scheme, we replace this by less accurate. So, d phi I by dt. So, this one is computed by phi I plus I minus I minus 1. So, this forward differencing because actually backward differencing, it is backward difference. No? So, I am taking the derivative by using only 2 points, but I am using a point behind me. So, backward differencing scheme. So, I minus I minus 1. Now, this is not this is less accurate than that. Error is the order. So, this first order scheme. Okay, so you can figure out error. This second order scheme. This we did in my when I was trying to do derivatives. Now, this scheme I can do the analysis, same analysis. Now, I will just write down the answer. Okay. So, if you do all the algebra which is there in the notes, so you can just redo it. It is stable for C delta t by h is less than 1. So, it is stable. So, if I choose my delta t, or so let me just put this stable if less than h by c. In fact, it is quite sensible. This is what physically people argue. So, how much time will the wave take to cover the distance h? H by c. So, your time must be, your delta t you should choose should be less than the time required for the wave to move. Okay. This anyway from dimensional analysis, this my delta t must be, but it comes out that to be conditioned from this Upwind scheme. Okay. So, dimensional analysis does tell you what should be delta t, what should be delta h. So, this proof I will not do this. Okay. I think it is a good time to mention one more idea right here, then we will move on to more complex stuff. I want to do Burger's equation after this, but let me just do one more method which is stable. So, stability is an issue. So, I will do stability for this equation. Okay. I am coming back to this equation. So, this equation I am going to solve. So, it is same as diffusion equation, but I want to choose my bigger delta t. Now, delta t is, this is really bad. Okay. H squared, I showed you the 10 power minus 5 is too tiny. So, we should choose delta t 10 power minus 2, 10 power minus 3, because h squared is 10 power minus 10, and that is now you are reaching the round of errors, okay, of the computer, precision errors. So, you do not want to choose such a small delta t. Sometimes you are forced to do it, you have no other option, but one clever way to choose bigger delta t is using implicit scheme. Now, I told all that not for just for fun. So, implicit scheme, so we can use implicit scheme which is called Crank-Nicolson scheme. Okay. So, this has generally more stable, means you can use delta t which is bigger. Okay. So, let me just, these are without proofs, but these are technology. This is what a numerical scientist should know. You can use bigger delta t, but also it has a price. it will be priced, you can immediately see what is going to be the problem. So, I had to use phi n plus 1 minus phi I n by delta t. Now, right hand side will be, now this should be computed at n and n plus 1, right. Implicit means I had to compute at unknown time, future time. So, this is going to be alpha by s squared phi I plus 1. So, the first part is 2 I n plus phi I minus 1 n plus the second at n plus 1. So, you have to divide by 2. So, there is a factor 2 here, because I am doing this computation 2 times at n as well as n plus 1 I plus 1 minus 2 phi I plus 1 no I n plus 1 is it okay. So, I compute this quantity at n as well as n plus 1 and take the average. So, this is called Crank-Nicolson scheme. Now, this is, of course, this equation is a linear equation, there is no phi squared, and you think that you should be able to solve it. But now, if I rearrange it, so there is a n plus 1. So, unknown is in terms of unknown. So, it turns out it becomes a matrix. Okay. So, this equation looks like, okay, now I do not want to write the full all the forms. So, it becomes y. So, I am going to tell you what is y in a minute. Phi I minus 1 n plus 1 plus x phi I n plus 1 minus y phi I minus 1 I plus 1 n plus 1 equal to right hand side, which only function of n. Okay, I will give you the notes where it is all calculated. So, this will function only of phi n right hand side. Okay, all the phi, this will be in the right hand side, all these will be right hand side, and this also will go to the right hand side. Now, this we can write in terms of matrix, right, because so how many unknowns are there? I have n unknowns, but of course, you can take the boundary out if they are known. So, you can write this in terms of matrix. Let us assume that both the ends are zeros, then my vector will be, so let us look at this point. So, this point will involve, so this is point 1. So, 1 will have 0 here and 2 here, and by the way, I should not solve the matrix for phi 0, phi 0 is already 0. So, I should not use that as a column in this matrix. So, my values will be phi 1, phi 2 up to phi n minus 2, not phi n minus 1. Now, phi 1 involves 0, but phi 0 value is known. So, that will go to the right hand side, presently it is 0. Okay. So, phi 1, so this is always 0. So, you do not need to put that. But, so, this is x. Now, x is function of h, okay, x is function of h delta t and all that, this capital X. If you want, I can just write these are all cumbersome equations. X equal to 1 plus. So, this is x and that will be y, this is n plus 1 with a minus, actually minus y. Okay. So, this will be phi 1 and this will be minus phi y phi 2, and rest all be zeros, and right hand side will be r1 r2 Is that clear? Not clear? Not clear? So, this equation I am rewriting, this equation I rewrite. So, collect all the terms of n plus 1 to the left. Okay. So, this so there is I minus 1 term, which is this I minus 1, this could go to the left, and that will give you minus 2 alpha by h squared delta t, correct. Now, what is n plus 1 n plus 1 for I? There is one term here, there is one term, this one is one term. So, that is one here. Now, this delta t goes to the right hand side, and the term here is this. So, 2 cancels and I get alpha delta t squared. So, that is x, this is coming to the this x. Now, phi n plus 1 I plus 1, this is a term which comes again to the left. Okay. So, all these terms are coming to the left. Now, what is remaining to the right? Which is known, you know what do you do in matrix? Ax plus Ax equal to b, b is known, x is not known, A is also known. So, this is known matrix, these are known, which is at n plus 1, and this is known, and all these guys, this one, this one, this one and this one will be in the right hand side. Okay. You have to just compute for i's and I plus 1. Is that clear? Now, so the next will be, if I look at point 2, so point 2 will involve 1 and 3. So, now this becomes x minus y minus y. Next will be, so 0 minus y x minus y, and this is, so this matrix has diagonal non-zero, which is all x, above will be minus y and below will be minus y, okay, and that goes away all the way except the first row, which has only 2 entries, and the last row also will have only 2 entries. Now, this you convince yourself, okay, all of it I will not do on the board. So, this is called tridiagonal matrix. So, if you want to solve this equation implicitly with bigger delta t, then you need to solve phi's, which is n plus 1, this is all at n plus 1, using a matrix. Now, you need to consider an algorithm or a computer program to compute the matrices. Okay. So, this we will do later, I will do this in the class, how to solve a tridiagonal matrix in a computer. It is in fact straightforward, but there is a scheme to do it. Okay. So, if I want to use implicit scheme by Crank-Nicholson, I am stuck here. It turns out I am going back and forth. So, if I want to solve this using implicit scheme, this scheme, then here it does not involve all these ideas. Why not? Spectral method, which I use mostly for my research, is it has lot of advantages, because my second derivative is not computed like this. I do not get a tridiagonal matrix. In fact, I get a very nice simple way to solve this equation. So, let us just do this again. So, if I want to solve it by implicit scheme, Crank-Nicholson, what should I do? So, phi k n plus 1 minus phi k n by delta t equal to, these computed at n and n plus 1. So, alpha k squared minus phi n plus y 2. Now, this is easy to solve, yes or no? In fact, this is straightforward to solve. I do not need any tridiagonal matrix. I take phi n plus 1 to the left, phi n to the right, and straightforward. Okay. So, this scheme, because the derivatives, the second derivative was this rather than that. So, this has easy solution for implicit schemes. Is it clear to everyone? So, spectral has, in fact, it has more accuracy. It definitely has more accuracy. Okay, let me just tell you, because I think my time is again running out. I need to cover. Yeah, I think I am almost done. Okay, I will tell you about spectral accuracy in the next class, but let me just try to cover now one more simple equation, Burger's equation, okay, which is going to combine wave equation and the diffusion equation.